Welcome to The Explainer. I am absolutely thrilled you're here today because we're going to decode one of the most common and, frankly, one of the most confusing phenomena in modern distributed systems. Today, it's all about replication lag and eventual consistency. If you've ever built a web app or, honestly just used one, you've definitely run into this. Okay, let's dive into this with a scenario. Have you ever posted a comment, refreshed the page, and watched it completely vanish? It's a terrifying moment for a user, right? You instantly think, wait, did I not hit send? Did the server just crash? Did my internet drop out? It's a completely jarring user experience, but it's incredibly common. Let's actually walk through the exact sequence of this social media glitch. First, you post your message. Second, you're eager to see it, so you quickly hit refresh on your feed. Third, and this happens completely unbeknownst to you, the system routes your read request to what we call a stale replica. And finally, step 4, you see your missing updates. Now, here's the secret. Your data isn't deleted. It isn't lost in the void. What you're experiencing isn't a bug at all. It's actually a direct architectural side effect of how large-scale systems are designed. So, to diagnose this, here is our roadmap. We're going to cover the stale data problem, understanding replication lag, read-after-write consistency, monotonic reads, consistent prefix reads, and finally, the consistency trade-off. Let's get into it. Section 1, the stale data problem. Looking under the hood of a distributed database. And this brilliantly illustrates the core architecture. To understand where our disappearing comment actually went, we have to look at how modern systems scale using leader-based replication. In a data-intensive application, a single server simply cannot handle all the traffic. It'd get crushed. So engineers designate one node as the leader. This leader handles all the incoming writes, all the data changes. Then that leader streams those changes out to multiple follower nodes. When users want to read data, like viewing a profile, the system can route them to any of these read-only followers. It's an absolutely crucial, incredibly effective way to handle massive read scalability. Section 2, understanding replication lag. Why followers fall behind the leader. Well, while leader-based replication scales reads brilliantly, it inherently introduces a delay. Copying data from the leader to the followers isn't instantaneous magic, right? We call this delay replication lag. So what causes it? Basically, real-world physical and system constraints. You've got network delays. After all, data still has to obey the speed of light traveling across fiber optic cables. You have high write volumes that can momentarily choke the system, nodes recovering from crashes, and temporary network outages. Because we usually replicate data asynchronously to keep the leader moving fast, the followers are almost always just a little bit behind. This brings us to the core definition of eventual consistency. Basically, it's the guarantee that if all writes to the database suddenly stop, the followers will eventually process their backlog and perfectly match the leader's data. Now, I really want to highlight that this inconsistency is just a temporary state. But remember, the word eventually is a deliberately vague promise. There is literally no strict time limit here. It could be a fraction of a second, or, if the network is really degraded, it could be minutes. Now, what's really interesting about this next topic is Section 3, read after write consistency. This is how we go about curing that disappearing bright anomaly. Let's look at exactly how hitting a lagging follower right after an update causes a user to think their data was lost. Say user 1234 writes a comment to the leader. The leader processes it, says, okay, got it. But almost immediately, the user's app reads from follower 2. Well, follower 2 hasn't received the replication stream for that specific comment yet. So what does it do? It returns an empty result. And boom, the user panics. So how do we fix this? The fix is an elegant solution called read after write consistency. We simply configure the system to route a user's read requests for their own modified data directly to the leader. We often do this by tracking the timestamp of their last update, and we keep this routing rule active for just a short window of time after they submit it. This guarantees that users always see their own recent updates, giving them totally necessary peace of mind. Meanwhile, they can still read everyone else's older data from the lagging followers, which preserves our system's massive scalability. Okay, on to Section 4, monotonic reads. This is all about preventing time from moving backward. Let's move to this scenario and see how this builds. Imagine you're user 2345. You check a page and your request goes to follower 1, which happens to have very little lag. You see a brand new comment. Awesome! Then you hit refresh. But this time, a load balancer randomly routes your request to follower 2. The catch? Follower 2 is lagging way behind follower 1. Suddenly, the new comment you just literally saw completely disappears. From your perspective, it looks exactly like time just went backward. No way, right? So the fix here is a guarantee known as monotonic reads. We can solve this time travel glitch by routing a specific user's requests to the exact same replica every single time they refresh, often by using a hash of their user ID. Now, to be clear, they might still see old data if their assigned replica is generally slow. But sticking to one single replica ensures they will never see older data after they have already seen newer data. Time only flows forward. Now for Section 5, Consistent Prefix Reads, keeping our conversations in order. Our final anomaly deals with causality and the logical sequence of events. Imagine a messaging app where messages are routed through different database partitions. Because of a short network delay on one node, a conversation might arrive totally out of order to a third party reading it. You might see a reply saying, yes, absolutely, and then, like 10 seconds later, you see the actual question, are we still meeting up later? It utterly confuses the person trying to read the feed because the fundamental law of cause and effect has just been broken. The fix for this is implementing consistent prefix reads. By tracking causal dependencies under the hood, often using things like logical clocks or version vectors, the system ensures that any related writes are always read in the exact sequence they occurred. So if message B is a direct reply to message A, the system strictly guarantees that no observer will ever see message B before they see message A. It totally prevents violations of causality, keeping those logical sequences perfectly intact, even if the overall system is lagging. Section 6, the consistency trade-off. After all of this, why do we even put up with replication lag? So, the crucial point is, you might be asking yourself, why do engineers accept these massive headaches instead of just using a single perfectly synchronous node and avoiding all these anomalies entirely? Well, it all comes down to a fundamental trade-off. We gain incredible benefits, high availability, and massive read scalability. But the costs are replication lag and major engineering complexity. The reality is, asynchronous replication is the only realistic way to scale modern web applications to millions of global users. You simply cannot serve the whole world from one single machine. Therefore, these consistency models aren't just academic exercises. They are absolute necessities to bridge the gap between necessary scale and a sane user experience. Given these trade-offs, which consistency guarantees will you prioritize in your next application design? Will you favor absolute speed and availability, or will you invest the heavy engineering effort to guarantee monotonic and read-after-write consistency? The choice entirely depends on what your specific users actually need. I hope this explainer gave you the structured knowledge you need to make that decision confidently. Keep learning, keep building, and we'll catch you next time.